Bring up, I'm going to start recording and I'm going to share my screen. So, can everybody see my slide? QRX should be visible. And because I'm sharing my screen, I'll need verbal because I can't see the participants anymore. I
Yes,
see.
yes, we can see it.
Awesome. Great. Well, welcome everyone to the QRX Quantum 101 lecture series. My name is Joan. For those of you who don't know me, I'm the Deputy Director of Education and Workforce Development at QSense, also the founder of the Quantum Ethics Project. And in this capacity, I'm working as the program manager for the QRX program. And, Mike Bennett, our director, had asked me if I could create a series of lectures for folks with absolutely no technical background discussing quantum and quantum technology. And the goal of these lectures is to get you all conversant in quantum technology, which is a term that essentially means you're familiar with the basic topics. You can have a conversation about them, but you don't necessarily need all of the mathematics, all the technical background, knowing what's underneath the hood. I like to give the analogy that I'm here to teach you about what color the car is and how fast it drives. And if you want to understand how the engine works, that's a whole other conversation. So with that, let's explore quantum. So today we're going to be asking very big picture questions, and I'm going to give a broad overview. What is quantum technology and what does it do? So first off, I'd like to just answer the question, what is quantum? We have everyday macro scale objects like cars and coffee cups and cats in the top left corner. Those are not what we would consider quantum. The word for those would be classical objects, objects which you can think of as having definite positions and definite momentums. They are places, they're going somewhere, and all of that feeds into our natural kind of intuition about how the world works. But when you start zooming in to smaller and smaller scales, you find objects that begin to behave very differently than the classical macro scale objects that we interact with every day. And so molecules, that's where you first, I would say, start to interact with some quantum properties. Molecules themselves, in terms of their own position and momentum, I don't think people typically think of those as classical objects, these kind of webs of atoms. But at the molecular level, you do begin to see the effects of quantum phenomena. And certainly in the bottom left-hand corner, when you get to the scale of atoms, or if you zoom in even smaller, on the bottom right-hand corner, I have a list of all of the particles that have ever been discovered. These are the particles that make up all of the matter in the universe, all the matter that we typically interact with on a day-to-day basis. And certainly at the level of atoms and at the level of elementary subatomic particles, that is where we see the majority of quantum phenomena beginning to become realized. And so I want to dig into this a little bit. This standard model, many of these particles, like the charm or the strange quarks or muons or taus, may sound very exotic and unfamiliar. But really, you can make every single atom on the periodic table and every molecule from there using only the three elementary particles that I've circled on the oval on the left. So you need electrons. We're familiar with those, I think. Electrons are the negatively charged particles that surround many atoms. And you need up and down quarks to make up the protons and the neutrons that are at the nucleus of atoms. And typically, when we think of atoms, the periodic table lists every atom that we have discovered thus far in science. And if you talk to people who took chemistry courses 50 to 60 years ago, their periodic table had fewer elements on it because this is a growing list of exotic atoms that we have made. But the basic idea is pretty simple. The different atoms are characterized by how many of the red protons, which you see on the left, that are in their nucleus. Typically, for the atom to be stable, they'll need neutrons to complement those protons. But the bottom line is the difference between carbon and oxygen is just two protons. Add two protons to the nucleus, and you very fundamentally change the chemical properties, the behavior of that quantum object. And then I had this figure here. Inside of a proton, you see those up quarks, two up quarks and one down, and inside of the neutron, two down quarks and one up. This is just showing you how the three elementary particles I mentioned, electrons, up quarks, down quarks, those are the three particles that make up every single atom, every single material that we have ever discovered. And quantum phenomenon help us understand how do these atoms, how do these protons, how do these neutrons, how do these electrons, how do they behave? And a final thing I'd like to say is that when we imagine an atom, the traditional picture is something like a solar system, with the nucleus at the center, kind of like our sun, and the electrons orbiting around, like the planets in our solar system. And the first thing I want you to take away about what is quantum is that that picture of billiard balls or planets orbiting around each other is completely wrong. And I'd like us to take a moment. This is one of my favorite videos of all time. This is a really nice visualization of the simplest atom we can look at. So looking back at our periodic table, in the top left corner is hydrogen, the smallest and simplest atom there is. It's the smallest atom because it only has one proton, and sometimes it has an electron to come with it. Not always. Sometimes you see a hydrogen ion. But this is what we want to do is picture what does a single proton, single electron, what is the simplest quantum object that we can think of? What does that really look like? And what is different from the quantum world to the classical? So let's take a look at this for a sec.
We don't have a sound.
On one hand, you have simple cartoon diagrams. Can I ask, can folks hear the recording?
It's a little bit low.
It's low, but you can hear it?
Yeah, I think they just started talking.
Okay.
Which are so varied and vague, they don't really convey much beyond the basic idea that atoms have a nucleus and some electrons. Some people try to take the cartoony diagrams and make them feel more random or quantum, which is an improvement, but they're still very much just cartoon stand-ins for the vague idea of atom. On the other hand, you have atomic orbitals depicted as fuzzy clouds or balloons or rainbow donuts, which are definitely more technically accurate or technically inspired, but none of which feel like they give you a sense of what's actually going on. Like, what does this blobby thing have to do with orbiting electrons? Is the electron inside it or on the surface? Why do some of them have blobs and others don't? And why are some of the donuts rainbow colored? I want to know what an atom looks like, and I want that picture to actually have something to do with the nitty-gritty reality of atoms, since they are things. You know, like how a diagram of the solar system is both a totally not to scale caricature, and yet also represents the very real idea that the planets all orbit the sun in roughly the same plane, and that some are farther out. If it's animated, we get to see the closer planets more often. It's a nice picture, and that's what I want for atoms, a good picture. There are a few things I'd like that picture to get across, some of them because they're important to the physics of atoms, and some of them because they're questions my brain wants answers to. Like, where is the electron? How fast is it going? How much energy does it have? How big is this picture relative to other pictures? Of course, the wave-particle nature of quantum mechanics means some of these ideas, like the electron's position, don't translate exactly from our everyday intuition to the atomic scale. But there is a way of thinking about wave-particle duality where you picture the wave function as a bunch of water and the particle as a speck of dust in that water. The particle is mostly guided by where the water goes, and the water is guided by the equations that determine how water behaves depending on circumstances. And if you apply the mathematics of that idea to atomic orbitals and then render it in 3 dimensions, here's what you get.
I absolutely love these pictures. This is what we're here for.
made a bunch of these, and they're all mesmerizing, beautiful. And isn't the ground state of the hydrogen atom just so cute? And aren't the excited states so majestic? There's so much structure and detail in them, I just love it. You can see patterns in the orbitals. You can get a sense that they actually are orbitals. I mean, something else orbit. Okay, so I do have to be clear. The dots don't each represent a separate electron. The whole collection represents the wave function of a single electron, and the individual dots represent all the places that electron could be. Higher density of dots means a higher probability of the electron being there. The bigger orbitals are the ones with higher energies, because electrons with more energy are more likely to be farther from the dots. The motion of the dots is showing the flow of the wave function, and does correspond to an extent with its actual angular momentum, though they're not electron trajectories. Unless you think Bohmian trajectories are real, in which case they really are electron trajectories. I'll let the philosophers of physics fight that one out. But the point is, these visuals are created by representing actual electron wave functions in a visual language that our brains can understand, that of objects and light and shadows and motion in 3D space. There's actually stuff orbiting, and they're really. I hope you like them as much as I do.
So just again, as a reminder, that cloud of dots represents a single particle. Questions? What questions do people have? We'll pause here for a second.
It's
So
like the
Yeah, go ahead, Abby, and then Pavel.
it's like electron geometry pretty much with atoms, kind of.
Yeah, it's showing you that at the quantum scale, electrons shouldn't be thought of as little balls with a specific position and momentum. They are probability clouds of all the possible places you might find the electron. But before you look for it, it exists in this novel, unique quantum state that doesn't have any sort of classical analog. Yeah, great question. And Pavel.
well, in that sense, with what you have answered, it means this cloud in reality doesn't exist. We only have one tiny little ball somewhere in this cloud, but in reality, it's not even a cloud. It's just it's just the idea where this small ball can be. Am I on the same page?
Yeah, I mean, you're in very good company. If I understood you properly, you're saying that the cloud is just an idea, and the electron is really somewhere. We're just not sure where. Is that what you're saying?
Yes.
Yeah, so you're in good company because that's how Einstein interpreted quantum mechanics when it was first being developed. We will show later on that it's even more interesting than that. And what I mean by that is I want you to try and wrap your head around the idea that a quantum object like an electron, it doesn't exist in the way that we typically think of objects as existing somewhere at some time with some momentum. So it's not that the particle is somewhere, we just don't know where it is. The property of being somewhere doesn't exist for the electron until you look at it. This cloud of possibility is all that exists for the electron. In the quantum world, the way I try to communicate it is in the quantum world, the notions we have of existence don't really apply. They have their own way of existing down there. And it's one of my favorite things about quantum is spending a lot of time trying to wrap my head around what that could possibly mean. And if it doesn't feel like it totally makes sense right away, that's kind of the point. But we will actually come back to that idea that you brought up, Pavel, of the particle having some definite position. We just don't know where it is because it's going to be important for the later discussion. Really good job, everybody. Any other questions before we move forward? I'm going to take crickets for a no. Okay. So we've just talked about what quantum is. So then what is quantum technology? And the first thing I'll say is that quantum technology has been around for just under 100 years. It sits at the foundation of technologies that we use every single day. Lasers, MRI imaging, the transistors that make your phone, the internet, this Zoom call possible, as well as nuclear power, nuclear weapons. All of those technologies were developed through our understanding of quantum phenomena. So let's understand lasers for a second. And to do that, we are going to turn to one of my favorite books. I got this, I couldn't resist when I saw this on the bookshelf. Quantum Physics for Babies by Chris Ferry. Lasers use a very basic property of atoms in order to work. So we have to understand a little bit what that property is. So we've just seen the solar system model of an atom, and we've just seen beautiful illustrations of how wrong this model is. But it is still helpful to visualize how much energy an electron, which is the green dot, has as it is in orbital around the nucleus, which are the purple and the red dots. So the key idea that we're going to take away from this is that the energy of the electron is discrete. It can exist at the bottom, the lowest possible, or the ground state energy, as is shown in the picture. It can transition to a higher energy, but it can't exist in between. That's a uniquely quantum feature. Typically, you can charge a battery between empty and fully charged and anything in between. But if if the energy in your battery was like the energy in an atom, it would only be able to be a third of the way charged, 2/3 of the way charged, or fully charged. So that's a little bit of quantum weirdness. And so you can imagine if you want to bring your electron to a higher energy, you have to add energy to the atom. And the way you typically do this is by hitting it with a photon, shooting a particle of light at it. And the atom then absorbs that photon, and the energy of the electron jumps to that higher level. Similarly, the energy of the electron could decrease. So it's a bit more of a technical diagram, but it's just the same thing. So the energy of the electron is in the higher position on the right-hand side, and now it's going to drop down to a lower level. And if you're able to raise the energy of an electron by adding a photon in, what do you suppose happens when the energy of the electron drops? What do people think? You put a photon in to put the energy up. What happens if the energy drops down?
It's either photon released or we have
rele-
release of energy.
Exactly. It releases a photon, releases energy. And because the energy levels of an atom are discretely spaced, they're a set distance apart, which we can denote with this delta E term at the bottom. The energy of the photon will be the same every time if the electron transitions from energy level 2 down to energy level 1. And does anybody know what happens if you change the energy of light? What changes about the light?
Wave or color?
Yeah, it changes the color. So what we're looking at here, the principle that lasers use to work, a laser is a device that emits light at a constant color, a constant frequency. So what they do is they prepare this device, which has electrons stored in this higher state, so that when you activate the system using this process called stimulated emission down at the bottom, you emit light at the pre-set or pre-desired frequency or color. That's how lasers work. And a funny anecdote is that when lasers were invented, no one had any idea what they should be used for. And a lot of people criticized the inventor of the laser as saying that they had invented a solution that was looking for a problem. It's kind of nifty. People have questions about lasers? We're going to move forward. No? Okay. So the next technology we're going to look at is MRI imaging. So if you've ever been in one of these things, it's basically a giant donut, and you stick your head in there or some part of your body, and then somehow the machine is able to image your tissue. And this is very helpful because it's completely non-invasive. And the principle that they use um, to use MRIs utilizes another property of quantum. So again, we just saw the discrete level energy levels of the atom as our first quantum phenomena that we can exploit as a technology. And the next quantum phenomena is the magnetic spin of the atomic nuclei. So let's take a look at this little video here. So let's remember an atomic nuclei is that collection of protons and neutrons. And each proton, each neutron has its own little magnetic field. And when you put them all together, the nucleus of the atom, it acts, collectively like a bigger magnet.
Own radio frequency signal in the process. This is what the scanner does. But it doesn't last forever. After a certain amount of signal from the nuclei away, and the amount of time it takes for the signal to die out is different for different tissues within the body. It is called T2, thus the process is called T2 relaxation. This is one method of providing a tissue contact. Finally, the nuclei will eventually realign with the field, and the amount of time it takes to do this is also different from one universe. So this process often spreads over, detecting their emitted signals and waiting for them to realign over, until enough signal is detected and produces a Now, the key to understanding the NMR phenomenon lies in one very simple equation called.
So we're going to pause it there. But the bottom line is that quantum gives us the ability to understand this T1, T2 time, which how these different atoms respond to the NMR process. And this is the way of, different atoms in a molecule, different types of molecules, making up proteins, making up tissues. This is how people provide tissue contrast within the body. Questions on this? I'll actually get, if people don't have questions, if you could just pipe up and say no so that I know how long to wait.
Or here's a weird random thing about MRIs. The way that it's formatted with the way that it has the quantum, I believe that's why you have to stay very still to get a clearer image.
Yeah, that's a good point. So the machine actually does this. It provides a magnetic field, aligns all the magnetic spins, and then it knocks them over and watches their T1, T2 processes. And then it does this several times to collect as much data as possible and to be sure that it's collected the correct T1 and T2. So, but if you were to move, it would start the process all over again because the machine wouldn't know if you had a particular piece of tissue in one spot. If you move, then that area would be giving off a different NMR signal. This is a great point, Abby. Other comments before we move forward? All right. So, again, what we're just covering what quantum phenomena are leading to different technologies. So the only thing you really remember from this is that discrete energy levels make lasers and magnetic spins make MRI, you're in good shape. Okay. Next, we're going to talk about transistors. Who can give me an example of a technology which relies on transistors?
TV,
TV.
remote
Good.
control.
Remote.
Your phone.
Earphones. Yep. Basically anything with a computer chip, any kind of electronic device that uses a computer chip, they use transistors. So these are, truly, this is an example of a quantum technology that has completely changed the face of society. And the phenomenon that we use to understand to understand transistors is actually, so we've actually covered this for the folks who were part of the hackathon. We played a game called the NAND game, where we learned how to build basic logic gates. And the transistor can be used as a basic NOT gate. It will allow current to pass through it if it's on the 1 setting, and it will prevent current from passing through it if it's on the 0 setting. So developing materials which can change whether or not they allow current to pass through them, which are called semiconductors, that relied on our understanding of quantum theory to become possible. And so the transistor relies on semiconductor technology in order to work. And we're going to watch a little video about transistors.
What would you say? Planning would make the case for fire. Our species was in an evolutionary rut until we harnessed its power. It gave us the warmth to survive harsh winters. Its light extended our day. Its destructive powers gave us a weapon against predators, and it allowed us to cook our food, which allowed our brains to grow. Our discovery of fire transformed not only our technologies, but our culture and our way of life. But I would argue that we are currently living in a time of equal or even greater change. We are living in a time of incredible growth, one that has already started to transform the way we live our lives. The age of information. With 40% of the world's population currently connected to the internet, the human race is more intertwined than ever before. But what led to this amazing tool? What single invention gave rise for a smartphone-equipped generation? The transistor. The transistor is information itself. Even this video is a series of ones and zeros beaming across the planet to be interpreted by the processors in your computers. Without the transistor, I wouldn't have access to the wealth of information online to do my research. I wouldn't be able to use my animation software to make these videos, and I certainly wouldn't be able to share it here for the world to see. The transistor is so simple, but it is the foundation of all our modern computers. To understand its input, you need to understand the history and science behind it. Before the transistor existed, we used vacuum tubes, which are these bulky evacuated glass bulbs. The triode vacuum tube consisted of 3 parts: cathode, grid, and anode. The current is passed through the cathode, and it begins to heat up, causing it to release electrons. As gases have been removed from the tube, the electrons have very little resistance to their movement, and they are attracted to the positively charged anode. This completes the circuit, and a current flows. But we can manipulate this flow of electrons in many useful ways with the grid. For example, we can use it as a switch. If we place a light bulb here, it will only light up when there's a positive voltage across the grid. If we apply a negative voltage, the negative charge will repel electrons trying to pass through. This is the foundation of binary coding, which is the ones and zeros that gave birth to the age of information. Here, 1 is a positive, 0 is a negative. 1 turns the light on, 0 turns it off. The world's first general-purpose electronic computer, the ENIAC, used 18,000 vacuum tubes to perform calculations. Designed by John Mott, J. Presper Arthur, it was completed in 1945. It was purpose-built to calculate trajectories for artillery during World War II. A calculation that would take a human a day to calculate, ENIAC 30 minutes. This thing weighed 30 tons and took up an entire room. It was incredibly power hungry, as the vacuum tube cathodes needed to be heated to work, which also meant that the vacuum tubes burnt out regularly, needed to be replaced. All this to perform a function that your phone basically does with anger trade. Today, its computing power could be contained on a silicon chip no larger than a grain of sand, and that's thanks to the transistor. A modern phone has around 2 billion transistors, perform the exact same job as the vacuum tube, but on the nanoscale. Let's look at how it works.
So I'm going to pause it there. A fun little piece of trivia. For folks who are in programming, you'll be familiar with the term bug. If you find a bug in your code, it makes your computer not work. The ENIAC device, which is basically a whole bunch of light bulbs, the team of computer technicians, which was led by Grace Hopper, who's one of the early computer scientists who programmed the ENIAC. The first ever bug was an actual moth that had crawled into one of the vacuum tubes, just the same way that moths are attracted to light bulbs on your porch, and had fried the system. And so there's a photograph of the first ever bug, which is a moth that's been taped to a report that Grace Hopper's team put together. I absolutely love that piece of trivia. Questions on this? We're going to move on from transistors now. But the basic idea is we were using vacuum tubes before, and now that we've got transistors, we can make a whole lot more of them. All right, moving forward. Okay. The final piece from the first quantum revolution that we'll talk about is nuclear power. And it really followed from Einstein's original kind of theoretical results, the famous E=mc² equation. It is so famous because it showed for the first time that you could convert small amounts of mass into relatively massive amounts of energy, and that became the theoretical guiding principle behind the eventual development of the nuclear bomb as well as nuclear energy. And I won't play a video. For folks who haven't already seen it, definitely watch Christopher Nolan's Oppenheimer. Really enjoyed it. But the bottom line is, nuclear power is a particularly potent example of a quantum technology that totally changed society again. You've got all these technologies we've just seen, very transformative, and nuclear carried with it a unique, uniquely destructive powers. And we'll kind of return to that, technologies having positive and negative impacts on society in a moment. But I'm not going to linger too long on nuclear power. The bottom line that I want you all to just come away is that the first quantum revolution, which began in the 1920s and continued on into the early 21st century, maybe the late 20th century, was really driven by our first journeys into the quantum realm and the phenomenon that were unique to that realm that we learned to harness and turn into technology. So discrete energy levels, magnetic quantum spin, quantum semiconductors, and the energy inherent to the nuclei of certain atoms. Those are the phenomenon that powered the first quantum technological revolution. And I say the first because the Quantum Research Exchange program and many other programs like it, we are today living through the second quantum revolution. And so today we want to really dig into, now that we've seen some examples of quantum technologies that are part of our everyday lives, what are these new technologies coming in the second quantum revolution? And that's a nice transition period point. Does anybody have questions before we move forward?
I do not.
Awesome. Thank you for the chime in. Moving forward, unless anybody's got to pipe up real quick. Nope. All right. So what is new? Well, if I wasn't clear, half of the first four technologies that I mentioned are either directly or very closely related to work that Einstein did. This guy keeps coming up. He's such a famous figure for good reason. But an interesting fact is that while Einstein was one of the driving forces behind the invention and development and discovery of quantum mechanics, certain features of quantum theory didn't sit right with Einstein. He didn't like them. They were uncomfortable for him. And as a result, some of the quantum phenomenon that are now powering the second quantum revolution, researchers and technologists, they stayed away from them, in part because of Einstein's influence, because it was believed for a long time that the phenomenon that we'll be discussing now about entanglement and superposition, that there had to be something wrong with our understanding of quantum. Einstein believed that entanglement couldn't be right. He called the quote that you'll hear in every video about entanglement is Einstein called it spooky action at a distance. And you can think of other examples of action at a distance in physics: the gravitational force, planets pull on each other from great distances away, the electric force, magnetic force. But entanglement was different. And Einstein felt that there had to be something wrong with the theory that predicted that entanglement was happening. And we're going to get into what exactly entanglement is and why he found it so spooky in a moment. But this wasn't the only quantum phenomenon that Einstein didn't agree with. There's the famous Schrodinger's cat, which many people are familiar with. It's very, prevalent in pop culture, which is intended to communicate the idea of quantum superposition, the idea that we actually saw in that simulation of the atom, where the electron didn't have a definite position. It was a cloud of possibilities. The cat is an example of two possibilities, alive or dead. And the idea of superposition is, whether it's with the cat or whether it's with the electron, is that the object does not have a definite state until it is observed. And this fundamentally means that quantum is a theory of statistics. It's a theory of probability. And that had a lot of philosophical implications that Einstein was just not comfortable with. Einstein didn't believe that free will existed. He believed that the laws of physics were definite, that if you knew the position and momentum of every single particle at the beginning of the universe, you could predict what Einstein would have had for lunch the next day. Einstein actually was famous for not taking credit for many of his greatest discoveries because he believed his actions were all predetermined. And this idea that the universe was fundamentally random or statistical or quantum was something that he didn't like. And another famous quote that he said was that God doesn't play dice. He believed that there had to be something wrong with a theory that predicts this kind of fundamental quantum uncertainty. And Pavel actually brought up the basic idea that Einstein believed would end up becoming true, which was that it's not that the cat is simultaneously alive and dead. It's one of the two. We just don't know which one it is. That's what Einstein believed. And it delayed the development of quantum technologies that harness superposition and entanglement for about 70 years, or there I'm giving rough numbers there. But it turned out that Einstein was wrong. And in fact, I think this is a little bit funny. He used to say God doesn't play dice. There's a company called Quantum Dice, which we'll talk about in a minute, where they actually, they embrace the idea of quantum randomness, and they have a technology, they have a patent we're going to talk about. That'll be our first example of a technology that uses superposition in order to work. So here's what we're going to do. We're going to go back to this well-worn idea of an atom with discrete energy levels. And we talked about this before in the case of laser technology. And when we were looking at the realistic simulation of the atom, a keen observer would have noticed that the particle cloud showing where the atom might be showed that the atom actually existed in multiple energy levels at the same time. So this is another this is the getting into that quantum superposition. And what we're going to do is we're going to imagine you have an atom with 6 energy levels, and the electron is equally likely to be in all 6. That's physically not terribly likely, but let's say we could engineer it that way. Then when we look at the atom, we're not going to find it in some weird quantum state. We're going to find it in one of those 6 energy levels. And so what we've essentially built is a quantum die, a 6-sided die. You roll it, and when it finishes rolling, that corresponds to you looking at the energy level of the atom, and then you know it's an energy level 4 or energy level 6. And so Einstein's idea was that just because you don't know which of the 6 energy levels you're in doesn't mean it's in all 6 of them at the same time. But what we're going to find is that the electron is, in fact, in all 6 energy levels at the same time. It's in this kind of pre-existence state we talked about, this kind of philosophical idea that quantum things have access to states of existence that we just don't have any experience with on the classical level. So we have this ability to build a dice, or quantum dice. And when I say Einstein was wrong, what I mean is that there is a fundamental randomness to the universe, that there's no way, even using quantum theory can tell you the likelihood that the die will come up on the side that says 6, but it can't tell you what side will come up before it happens. So how could we use this to build some technology? Well, that's where the Quantum Dice Company comes in. And you can Google them. They're a company based in Oxford. And their idea was this. If any programmer writes a program and you need to generate a random number, you'll say maybe random integer between 0 and 7, or between 0 and 6. The computer is not actually randomly generating a number. This is what's called a pseudo-random number because the code has to do something to come up with what number it should spit out. And that process, the code that the rand function uses to work, might be hackable. So imagine there's a company that sells casino games for like digital casino games. And this company has maybe online poker. This company has a vested interest in people not being able to predict what the next random card on the blackjack app is going to be, because otherwise they'd be able to make crazy amounts of money. They'd go out of business. Quantum dice is selling the inherent randomness of quantum things as a physically proven certificate of pure randomness. Randomness that can never, under any circumstances, thanks to the laws of physics, be predicted ahead of time. I'm going to pause there. People have questions about quantum dice. This is our first example of seeing superposition used to make a quantum technology. All right, I see Kara, no questions. Thank you, Kara. So here's the basic conflict that, Quantum Dice could have been a company that was founded in the 1950s if Einstein hadn't held up the works, if he hadn't slowed us down. He did a lot of things. I'm not trying to throw shade. Einstein's one of my favorite people. Anyway, here's the basic conflict. There was an equation that basically captured the two ideas. If the equation, which we see above Einstein's head, resulted in a number that was less than 2, that would mean Pavel was right, that the electron is somewhere, we just don't know where. The cloud just represents our ignorance, but the electron must have a definite state. And the picture of the gentleman on the right is a famous physicist named Bell. The equation above him is called Bell's inequality. And Bell came up with this idea for an experiment that would say, if the number is less than 2, Einstein is right. If the number is greater than 2 or equal to 2, then the quantum nature of superposition is that it's fundamentally random. And it wasn't until the, I think, early 2000s that this experiment was verified. And in fact, the Nobel Prize, I think in 2022, very recently, the Nobel Prize was awarded for the people who found that it was in fact Bell who is correct, that the Bell inequality showed to be greater than 2. That tells us Einstein was wrong. The atom is fundamentally random with its energy levels, and now you have quantum dice. They have a patent. They can now say, I'm selling pure quantum randomness to anybody who wants it. And that experiment that showed Bell's inequality was greater than equal to 2, it kind of set off this new quantum revolution, this second quantum revolution. There were other factors as well. But this is what helped people embrace the ideas of superposition and entanglement as well. It has implications for entanglement. In fact, entanglement was the main subject of the experiment. So let's get into, now we've talked about superposition. We're now going to talk about what entanglement is and why Einstein thought it was so spooky. Okay, so we just talked about how Schrodinger's cat is truly alive and dead at the same time. So let's imagine now you have 2 Schrodinger cats. I like to think of it as, 2 quantum coins. I don't particularly like Schrodinger's cat. It's kind of gruesome for me, but it's because it's so prevalent in pop culture. We're going to work with Schrodinger's cat. So if you've got 2 Schrodinger cats, and let's say you set the experiment up, they're both in 2 separate boxes right next to each other, and then you take them into 2 opposite rooms of your house. If you've got 2 people who are going to look in on the box and tell whether the cat is alive or dead. You've got 4 possibilities. Both the cats are alive. One is alive, cat A is alive, cat B is not, or cat A is not and B is alive, or cats A and B are both not alive. So 4 possible options. The same sort of thing if you flipped 2 different coins. They could both come up heads. You could get heads and tails. You could get tails and heads, or you get tails and tails. What entanglement allows you to do, given the fact that these are still fundamentally pure quantum random outcomes, is you can make sure you can set up an experiment so that your 2 coins will always either both come up in agreement or in disagreement. So let's say both coming up heads or tails. So if you have the cats in superposition and they're now entangled, when I look at the first cat in my room, I flip my first coin and it comes down heads, I know for sure that your equally random cat will also be in the heads state. It'll be alive. Or if I flip it and it comes down tails, I know for sure that the other one will come down tails. And the reason Einstein called this spooky action at a distance is that this agreement of the random states happens immediately, instantaneously, no matter how far separated the 2 cats, the 2 coins, in the case of Bell's inequalities, they were photons, how far apart those entangled pairs happen to be. You can always make sure that they are in agreement, while also knowing always that the outcome of the measurement is completely random. I'm going to sit with that because that's a fundamental, profound, and philosophical piece that, we're getting towards the end of the lecture. Folks may be a little bit fried. I want to pause with this for a second and just come back to this idea that if you have unentangled or uncorrelated randomness, you could have all 4 possible cases of a 2-option system, like a coin toss. And with the entanglement, you reduce that space to a size of 2. They'll always agree, they'll always disagree. Do people have thoughts, questions, concerns? Do you agree with Einstein that this is spooky? Do you not like it? What do you think? What do people feel about this?
I think I kind of agree with Einstein. It's very spooky and kind of like hard to wrap your head around that with like an entanglement, you have 4 options, but when it's entangled, once you get one like answer, you know that it's entangled with the same kind, if that makes sense. So like if you get A, you know that it's going to be A for the second one, and if you get
Yeah.
D, you know it's going to be D for the second one.
It's totally bonkers. You're absolutely right. And, we could get into a big philosophical discussion. I have lots of thoughts about this, but the basic, mystery here, I think we should just appreciate it for a second. This is totally different than anything we have experience with in the classical world. And I think that's just amazing. I think quantum just has so much to teach us, so much we can learn from things that can be in these sorts of novel states of existence that can allow for entanglement and superposition. I just think it's delightful. Okay, here's what this has all been building to. For the first quantum revolution, we talked about 4 different quantum phenomena that led to technologies. And now that we've resolved Bell's inequality and we are ready to technology, build technology from principles of superposition and entanglement, this gives us 3 new kind of core pillars of quantum technology. And this is not an exhaustive list. People might break it down into a list with 4 or 5 or 3 or maybe more distinct technologies. But I like to think of it as having 3 core pillars: computing, quantum computing, which I think many people may have heard of if they're in this program. Quantum sensing, which QSense, the program that funds all this work, is focusing their research efforts on the middle pillar. And quantum communications, and the image I put there, think of quantum communication researchers as they're trying to build a new kind of internet that can communicate these sorts of entangled, superimposed states through optical wires or through satellites. And all 3 of these technologies, many of them, if not all of them, utilize quantum entanglement and superposition to do things that we couldn't do before, because we don't have the access to those resources in the classical world typically. So in future lectures, we will focus on each of these in detail. But as we're getting towards the end of the presentation today, we started a little bit late, so I might go about 7 or 8 minutes over time. I want to give a quick overview of what do these technologies do? Why are people building them? What are people excited about these technologies being capable of? Quantum computing is the area that I know best. It's from my own graduate studies at the Institute for Quantum Computing as a master's student. And my specific research focused on the top left box of machine learning and AI. People want to use quantum computers to enhance machine learning and artificial intelligence systems, which already sounds like crazy future sci-fi stuff. There's also some not so great applications. The very first quantum algorithm, which was discovered and triggered a big wave of investment in quantum computing, its only application was destroying the security that our entire internet is based off of. So it doesn't really have, as is called, Shor's algorithm, and in my view, it doesn't have a single positive application. And then there's others: drug discovery, finance, chemistry, logistics. There's many areas where people are hoping quantum computers will be able to solve problems faster than a traditional computer. Not to say that they can do everything faster. They're actually terrible at adding numbers. I gotta say, you can do it, but they're really bad at it. So there's a couple special applications that quantum computers are believed to potentially add some benefit. Then, after computing, we have quantum sensors, and people are hoping to use these, for example, for navigation. So Inflection, who sponsored the QRX hackathon, is trying to build a quantum sensing device that does not use GPS and can help you navigate without a GPS satellite. So there are some that can be used for detecting oil and natural gas deposits, which in my view is, again, one of those not so great applications. I think the climate crisis is a big one, and but that's a kind of a personal view. And there are many other applications, medical scanning, making the resolution of things like MRI machines sharper to detect medical issues more effectively. Lots of different areas for quantum sensing to add some value. And finally, quantum communications, the kind of signature application of the quantum internet is perfectly secure communication. So similarly to the way that superposition gives you perfect random numbers, you can use quantum phenomenon to be able to send a message and always be able to know if someone is eavesdropping on your message. It's a way to ensure that you can always be sure to have a secure communication line. There are other applications, some of these technologies enhance each other. So the quantum communication technologies are also, many people want to use them to assist quantum computers to network a bunch of computers together to make a bigger computer, things like that. And we'll dig into some of these in greater detail in future lectures. But a big takeaway that I need everyone to understand is that none of these technologies work. And when I say they don't work, I just mean they aren't yet able to do something that we can't already do with a classical technology. Quantum computers can solve simple problems, but nothing that my laptop can't handle. Or nothing that a supercomputer can't handle. Similarly with sensing and communications. So we're still in the phase where these technologies are very young. Quantum computing is the oldest, and it's only as old as I am. It's 28 years old, if you date it by the date that Shor's algorithm was published. So these are very young technologies that still have a long way to go before they are changing society. But and that's something that I want to make sure people understand. If you're hearing articles about quantum computers enhancing AI and taking over the world, people are talking about 50 years in the future, a long time from now. Obviously, I can't predict the future, but the bottom line is it's not working today. And the final thing I want to, touch on, we briefly touched on this, but technologies, I want to talk about not just their applications, but the fact that they have good and bad uses. And we see this, right? Transistors led to the internet age, and you've got freely accessible information. You can learn anything, basically. Wikipedia is a great resource, but you also have the phenomenon of social media mental health crisis. With nuclear, the issue is even starker, I think. You've got carbon-free energy on one side, which might be radioactive, but at least doesn't contribute to the climate crisis, and nuclear weapons, which for a time and still potentially threaten the existence of life as we know it. And that's a pretty big divide. And with the quantum technologies that we have today, there are similar sorts of issues and concerns. And this is an area that I specialize in my scholarship, which the area that I do work in for the quantum ethics project that I mentioned at the beginning is, quantum ethics is the field of study where we think about the social impact of these technologies. And we try to think about how do we develop these technologies for the greatest and most equitable public good. And for equity, a Google definition was just saying that equity refers to fairness and justice and is distinguished from equality. I think the best way to capture what equity is using this image. So there's a fence which obstructs people's view of something they'd like to see. And equality would be to help everyone equally, even though three different people, three different heights, some of them don't need support. Some of them need more support than others. So equity is the idea that not just treating everyone equally, but treating everyone with the support that is proportional to the need that they may have. And I like to also contrast this with the idea of justice, which is to remove the barrier altogether. But that's a separate discussion. I do want to keep respectful of folks' time, so I'm going to move a little bit quicker towards the end of this. But the idea here is that we have the opportunity at this early stage of quantum technology where these technologies are still being shaped by everyone from, PhD level scientists to the technicians and the lab workers that, you all are in this program to try and get an internship. That's even at that level, you have a say in how this industry is formed. At least in my work, I try to ensure that I find ways to promote the equitable use of quantum technologies. And so we're going to end here with a spotlight on the applications we mentioned before. With a quantum computer, you might see drug discovery, discovering new medicines. Banner application might be cure cancer. Curing cancer with a quantum computer would be amazing. I don't think I can really make a case that that's a bad thing. But cyber terrorism, not so great. With sensing, you could use it to help, again, in the medical space. With finer resolution, maybe the MRI machine catches a tumor when it's just barely forming and easy to fix, versus contributing to the climate crisis. Maybe not so great. And for quantum communications, secure communication sounds great. But we didn't get a chance to talk too much about blind quantum computing. But there's gray areas with all of these, and there's no right or wrong answer with many of these. And if we were in person and if we had the time, I would run a whole workshop discussing the merits of various things. But I'm going to leave you on this slide with a quick example, just as a thought provoker for the end of this lecture. Imagine we're going to apply a quantum computer either for finance, we're going to optimize someone's investment portfolio, or for chemistry, we're going to use it for that drug discovery application that I mentioned. And there's actually two quantum companies that I heard of a few years ago that were looking at doing just these things, finance and chemistry for each of these. But quantum computers are going to be rare for a long time. And maybe only one company, maybe Google, will have access to a quantum computer that can solve these chemistry or solve these finance problems. And the idea is, which application are they going to choose? Are they going to choose to cure cancer, or are they going to choose to give the wealthiest hedge funds in the US more competitive investment portfolios? Just comparing the size of the industries. If Google's it's a corporation, so it has a legally binding fiduciary responsibility to maximize investment for its shareholders. So it doesn't really have a choice here. If it can make more money, if the rich, if Jeff Bezos can pay them more to make him richer, then they can't legally choose the option that cures cancer. And so that's the question I'll leave you all with. It's a kind of a question that keeps me up at night. It certainly did in graduate school. We're building these new technologies, and who is ultimately going to benefit from them? We're going to stop there. Do we have final comments or questions? I'm actually going to stop the recording in case folks want to talk without having to be recorded here. So 1 second.